Greetings on behalf of the SAE SUPERMILAGE team. We hope you're staying safe during these tough times and making the best out of your time. Now, we will show you on what we have been working on for the past 6 months to be able to go for the extra mile. So, as a brief introduction, we will be talking about our project and our project goals, as well as the work that has been done by the Powertrain and Chassis Division. Also, we will be showing some sneak peeks and future plans you might be interested in.
Greetings, my name is Guillermo Veloz, and now we're going to talk about the project. Well, our project focuses on minimizing the use of fuel for the manufacture of a one-person vehicle. The different variables that we will be considering to obtain a more efficient vehicle are weight reduction, engine modifications, and aerodynamics in the area where is needed. For the project, we have many ambitions that we want to complete. But in order to reach our future goals, we first have to manufacture a vehicle that will travel over 2,000 miles per gallon in order to take it to the SAE SUPERMILAGE 2022 competition, completing our first milestone. As a future goal, we will be opening another project for the Shell Eco Marathon competition, and we will also be competing in the next SAE SUPERMILAGE 2023.
My name is Julian Gil. I will be presenting the connecting rod modifications done to the engine. This was done to achieve the desired bore length, and a longer rod was needed to reach the cylinder sleeve, given that we had to reduce the diameter. To guarantee a tight fit, a cylinder sleeve was chosen and a jig was done for that. This connecting rod has the benefit to withstand the combustion pressure of 50 bars. It also has the benefit that it has a lower swept angle, which is 11.54 degrees, and that also means it has lower horizontal forces for the downstroke. For the connecting rod ANSYS analysis, a static loading and dynamic fatigue loading analysis was performed. On the static loading, we have the following values of maximum stress of 81.6 megapascals, maximum deformation of 0.2 millimeters, a factor of safety of 2.142, which is excellent. And for the fatigue loading, it has a cycles of 1.17 times 10 to the 6 and a factor of safety of 0.63, which is perfectly fine for the cycles and stress that our engine will endure.
Hi, my name is Carlos Rodriguez. I will be explaining the engine's jig and gasket design. The purpose of these designs is to reduce the piston bore to 39 millimeters to fit our selected piston. In addition, the distance created by the space between both parts makes it possible to use our elongated connecting rod system. As a result, the total distance between the two parts is equal to 58.45 millimeters. The assembly is composed by the gasket, which mates to the original engine block, and the jig part, which mates to the newly designed cylinder head. Heat transfer was considered and developed a design of various fins for heat dissipation.
Greetings, my name is Juan Núñez and I'll be talking about the engine's internal combustion. A process called material balances was used in order to calculate the fuel and air mass fractions of the entire combustion reaction. These mass fractions were used to complete the fuel composition label at the Ricardo Wave software with the goal of obtaining more accurate graphs of indicator specific fuel consumption and brake specific fuel consumption. The calculation bases used for this analysis were the following. All fuel reacted completely, and because of this, the vaporized fuel, the burnt fuel, and the liquid fuel had the same mass fractions. Air was not being fed at an excess. Unlike burnt air is the theoretical air that reacts with the fuel, then this would mean that burnt air and fresh air also had the same mass fractions. The numerical results of the material balances are displayed in this table. In order to know the energy released from the combustion reaction, we need to calculate the heat of reaction of the combustion process. The heat of reaction of isooctane is 5,461 kilojoules per mole at 25 degrees Celsius. 25 degrees Celsius is not our desired temperature, but because the heat of reaction is a state function, we can alter the path using our desired temperature to calculate our desired heat of reaction, which in this case is delta H2, As shown in the diagram, delta H1 represents the heat of reaction of the reactants, and delta H3 represents the heat of reaction of the products. We need to calculate both of them in order to solve for delta H2. The values at the data table are already given to us, and using this, we can calculate the heat of reaction of each species in the reaction. Delta H1 is calculated by adding up the heat of the reaction of the species present in the reactants, and the same is done for delta H3 but using the products. Finally, we can solve for delta H2, and that will be the energy released from the combustion reaction.
Hello, my name is Ricardo Bocachica, and I will be presenting the intake and exhaust manifolds and the performance curves of the engine. For the manifolds, the intake design will have a throttle system, and it will be facing to the coolest area of the engine. And for the exhaust design, it will be facing to the back of the car, and it will have an isolator to prevent vibrations on the chassis. Moving to the performance of the engine, here we have some parameters of the simulation in Ricardo wave of the original engine. With the parameters, we identified the brake-specific fuel consumption, torque, and power graphs, and since the lowest value of brake-specific fuel consumption marks the efficiency, a relation was made between all the graphs, and it was found an efficiency point in the indicator RPM with the indicator values shown in the table. Now here we have the specifications of the simulation Ricardo wave of the modified engine. We had a problem with the simulation since the peak torque and peak power could not be identified because the program does not identify the small bore that we have. However, the efficiency point is defined in the brake-specific fuel consumption, and the same relation can be done obtaining in the indicator RPM the values mentioned in the table. It is important to mention that these are theoretical graphs of the engine based on Ricardo wave, so they will be compared with graphs obtained in the dynamometer in the future.
The electronic valve train was presented as an idea for our vehicle implemented by solenoid and a map sensor. A solenoid valve is an electrically controlled valve. It has several benefits such as a variable valve lift that varies the height of the valve in order to improve performance, fuel economy, or emission. Also, variable valve timing and variable valve duration. Without any doubt, controlling the valve electronically is much more efficient, as you can see in the graph shown. Implementing solenoid has some downside, like cost and complexity, but the benefit is higher. In order to see the relationship between vehicle speed versus gear ratio, vehicle speed versus fuel economy, and vehicle speed versus power, some graphs were made. All vehicle speed were calculated by varying the gear ratio at a certain engine speed with a range between 2000 RPM and 3600 RPM. Our maximum efficiency and torque point can be found between the range of 2000 RPM and 3000 RPM. To obtain the vehicle's train and power and fuel economy, certain calculations were made, and efficiency including transmission of 0.51% was obtained, a drag coefficient of 0.1, a frontal area of 0.16 square meters, and a vehicle weight of 226 pounds. With a top speed of 25 miles per hour, which is where the most fuel is used, and 2500 RPM, where the maximum efficiency and torque is found. A power output of 0.23 horsepower and 4,919.7 miles per gallon was obtained.
Due to the desired reduction in displacement of the engine, a sleeve that will be inserted inside the original cylinder was designed. This sleeve is a 43% bore reduction, which would result in a 76% displacement reduction from 204cc to 70cc. This sleeve would also be made of aluminum and have fins added for heat dissipation and structural support. With this new bore, the cylinder head had to be redesigned. Originally, we bought one with the required bore, but it was too large and had too many components, so we opted for making our own to tackle these problems. We are going to implement an electronic valve train design which will allow variable valve timing, and having control over the internal head structure allowed us to implement bigger ports adjusted to fit our needs for the desired air-fuel ratio. By being electronic, many mechanical elements are discarded, resulting in a lower system inertia and less losses due to friction, along with a reduced weight. And here is a CAD of the resulting modified engine where the implementation of the cylinder sleeve, jig, cylinder head, intake, and exhaust can be seen attached to the motor.
The engine control unit, referred to as the brain, is divided into two main computing units, the Arduino Uno and the Raspberry Pi. The sensors listed here connect directly to the Arduino Uno, which then sends the data to the Raspberry Pi. The Arduino Uno is in charge of collecting the data from all the sensors and converting some sensors' data from analog signals to digital signals, to then send to the Raspberry Pi. The Raspberry Pi, in turn, uses the acquired data to manage the different systems of the engine. Also, the telemetry data that will be displayed in the cockpit is transmitted directly from the Arduino. Something to note is the speed map inside of the Raspberry Pi. Think of this as a fuel map, but for the speed of the car. The speed map receives inputs from the accelerator pedal and the vehicle speed to control the engine's RPMs and the CVT's gearing.
This graph shows the center of mass of our car calculated based on the weights of the different components, including the weight of the driver, which is around 135 pounds, the ideal, the weight of the engine, and the weight of the shell, which do not appear in the image. The center of mass is 810.2 millimeters from the front tire axis and 323.94 millimeters from the ground.
It is not a requirement of this competition to lock all tires during peak braking. For this reason and for their lightweight, hydraulic disc brakes are going to be used. However, it is important to decide which type of calipers are used, either 2 or 4 piston calipers. Because of this, the capacity of this type of brakes to produce deceleration has to be analyzed. And this equation was derived by summing moments with respect to the frontal wheel axle. Assuming all tires lock during caliper engagement is not practical because bicycle calipers are not that powerful. The transition from dynamic friction to static friction will vary depending on the decreasing velocity. But as soon as the calipers lock the disc, the tires experience friction, which will contribute an additional torque that the calipers have to sustain. And in the case they don't sustain it, the calipers then go back to dynamic friction. To model this transition is complex, so friction averages were taken. These graphs reflect the performance of the calipers at varying tire engagement. We also wanted to analyze how much effect the force at the master piston of the hydraulic system would have on performance. That graph on the left has data for a setup of 2 calipers each with 2 pistons, and the one on the right has 2 calipers each with 4 pistons. For this case, a low assumption of tire road friction was given in order to visualize a close to worst case scenario and rely on caliper performance more instead of relying on road friction.
Based on the distance between the steering joints and the wheelbase, we were able to calculate the Ackermann steering angle, obtaining 6.63 degrees. In addition, with other parameters considered, such as the maximum turn radius, we calculated the inner and outer wheel maximum steering angles. This result gave us 7.84 as the inner wheel maximum steering angle and 7.46 as the outer one. These pose as our ideal steering angles with the respect of the radius of the curvature. So through Anat's animation designer, we were able to use our assembly of the design steering mechanism to calculate the angles. So this generated many data readings that allow us to create this linear regression that you can see here. This help us determine how accurate our design steering mechanism angles will be compared to the ideal maximum steering angles that we calculated before, and as we can see on the graph, they are very similar.
Also, we wanted to analyze the maneuverability performance of the car during this slalom course. A sine function was used to model the lateral displacement oscillation. Given the time traversed two full cycles of curves, angular frequency was obtained and max lateral displacement was assigned to be the amplitude of the sine function. The parametrical equations were then put together to establish a relationship of lateral displacement with respect to forward displacement, and this way, the radius of curvature at any point could be obtained. With the pre-established kinematic parameters, then a dynamic analysis was performed. The centripetal acceleration was calculated using the max possible speed during this testing trial and the smallest radius of curvature. We wanted to analyze how the normal force is distributed given our car's geometry during performance.
In order to minimize the weight of the shell without compromising its structural integrity, we'll be using this formula. And so these proportions, 1.2 millimeter shell body can be designed using two layers of 2x2 woven e-glass clad of approximately 100 grams per square meter each, which contributes to the 0.3 millimeters of the thickness. It will be also important to mention that the shell body currently is designed to have approximately 5.45 square meters. So here we have different tables. The first one is the approximate weight of the proposed shell design. The second one is the different mechanical properties for each of the fiber types. And the third one is the current mechanical properties of this specific epoxy infusion resin that has a great tensile strength. So with the 25 to 75 proportion of the fiber epoxy, if you use the equation before, it provides a result for an unidirectional composite, which means that the fibers go all in the same directions. And therefore the approximate tensile strength achieved will be around 540 megapascals in the directions of the fiber.
For the analysis of our chassis, we have decided to go with an adhesively bonded joint instead of fasteners. This is because our composite beams are more prone to failure by shearing, which is mitigated by using an adhesive instead of a fastener. To prep for the analysis, it is important to set the tolerances and identify the contact and target bodies correctly to mitigate the overlapping errors. As you can see in this adhesive bonding toy simulation, it is done correctly and successfully withstands the loading on the composite member. The stress concentrations are generated on the adhesive body. In this image, the adhesive body shows the highest shear stress concentration of the whole joint structure, which leads to the conclusion that the analysis setup is done correctly and goes accordingly to the theory backing it up without any discrepancies. To model our composite members, we use the ACP model within ANSYS Workbench, in which after adding the mechanical properties in the Engineering Data tab, you are able to assign the orientation, layout, and thickness of your composite to a surface body within your assembly or work part. This enables you to experiment with different layouts and put to trial manicured products from the different manufacturers based on their safety data sheets, and pick the one that is most convenient for your application.
In this image, you can see a prototype of the shell. So far, it is not a final design, but it is more or less the idea we have. As you can see, the wheels are completely covered by the shell, and we are looking for a way to make the shell as finite as possible in the front part. This is for performance and aerodynamics reasons. Although this aerodynamic factor does not have such a significant effect since the speed at which the car travels is only 25 miles per hour as maximum.
During the semester, fundraising sales made by the logistic teams have mostly been on distance. From those, we have a net gain of $2,048. Unfortunately, we did not reach our objective by 2%, but new strategies are on the go. Our social media outreach has been via Facebook, Instagram, and recently LinkedIn. Posts regarding sales Recruitment, sponsors promotions, and team members' exposures have been done weekly. Statistics report countries outside of the island have visited our pages, which gives us opportunity for greater exposure. We are grateful to the companies that have helped us this semester. Their donations have provided us with materials and components to make the next semester's manufacturing possible.
We have noticed a great improvement in our members' technical capabilities throughout this semester. Therefore, the team administration has established a new goal. We would like to take our team a step further next year, which is opening a second team to participate in the Shell Eco Marathon Urban Class Competition, which is basically a super mileage competition, but the actual design of the vehicle should resemble a road-going car with its features and looks, further complicating the technical constraints. We know that there is the talent to carry on this task, so if anyone is up for the task, scan the QR code on the next slide. Now, we would like to thank you all for listening to our presentation. Now we'll be having a session to answer all of your questions and doubts. And remember, if anyone is interested in being part of the first Eco Marathon team in UPRM history, please fill out this form or contact us to the given directions.